Is Nathan Young, and I'm the Chief Engineer.
I'm Marlon Sevilla, and I'm the Project Manager.
I'm Brian Chen, and I'm one of the sub-team leads, and we're Design Build Fly. So Design Build Fly is a large-scale competition where teams from all over the world come to compete. There's over 100 teams competing, and we have teams all over the world from China to Hong Kong to Egypt, and even domestic teams such as MIT and Stanford. So the design requirements for Design Build Fly, the competition changes each year. And it usually varies between the hosts, which are Cessna and Raytheon. This year, the host is Raytheon, and they tend to favor military-designed aircraft. As a result, the design or the theme for this year is a carrier-based aircraft. The competition will be taking place in Arizona this year in mid-April.
Now, DBF historically has been a pretty formidable force in the competition. We've consistently placed top 10 within the past decade, with some highlights being listed over here. 2013, we got first place with this rocket-carrying short takeoff flying wing.
In 2014, we had a bit more of a conventional aircraft, but it had to carry bricks.
2016 was a modular plane within a plane themed aircraft.
And most recently, last year, where we had to play the game with a low aspect ratio passenger aircraft. So to keep with tradition, our objective this year for the 2018-19 team is to place top 3 in this year's competition in Tucson.
So as mentioned before, the design requirements for the competition each year changes. So at the beginning of the year, the organizers release a set of rules that are purposely vague to give all the engineering teams a bit of leeway to create innovative solutions to their challenges while also meeting with the design requirements. So as a team, we read through all the rules and we made note of like the very important requirements and listed them above. But to summarize, next slide. Some of the key points are that the aircraft wings for this year must be able to fold and unfold remotely. In addition to that, the aircraft must be able to carry a radome and have it rotating within flight. And lastly, the aircraft must be able to carry a minimum of 4 stores under its wings. So, the key points that I've just mentioned relates to the missions that DBF consists of. So DBF usually consists of 3 flight missions and 1 ground mission. This year, mission 1 is to complete 3 laps on the course as shown above within a 5-minute time window. Mission 2 is similar to mission 1, except we will have the radome installed, and we want to complete mission 2 as quick as possible to score a maximum amount of points. Mission 3 is the tricky part. So mission 3, we need at least 4 stores carried on the aircraft, and for each store that we're carrying, we must fly 1 lap per store. And then furthermore, we must drop 1 store remotely at a given location on the course per lap. And then lastly, the ground mission is just a race between assembly members to install the radomes and stores as quickly as possible.
So from the aforementioned missions, each have their own equation tied to them, listed on the right-hand side. At the beginning of the year, we constructed a score analysis to see what really drives this year's competition. As you can see, on the y-axis, we have the overall flight score versus the number of stores we carried. This is quite important because if we look at the equations for mission 1, M1, and M2 respectively, the most number of points you can get is only 1 to complete mission 1, and 2 if you're the fastest plane there is. But mission 3, on the other hand, is a little bit more open-ended. As Brian mentioned, we want to try and carry more stores because it's 2 points plus however many scoring laps you can complete. Hence, from the illustration, the gray bar represents mission 3. By carrying more stores, it has the highest yield to the overall flight score. Hence, the team will be pushing towards carrying as many stores as possible to maximize its overall score.
Now, the whole point behind this grueling and detailed analysis of the score and this horrifying score analysis process is to translate customer requirements into design parameters. In this case, our customer is AIAA, it's Raytheon. They've released a contract, and we're trying to bid to kind of give the best aircraft to fulfill their performances in the best way possible. For example, the aircraft must maximize stores carried. But what does that mean? By maximizing stores, we not only have to fly at a higher speed, but we have higher takeoff weights. Speed is pretty bad. The reason why is because power is a function of velocity cubed. For a linear increase in velocity, we have a cubic increase in power required. More power means more battery packs for takeoff. The aircraft must be stowed in a 3x2 by 2 foot box. Well, this clearly limits our wing area. A smaller wing area means higher wing loading. That means more forces and structure into our spar design. It also means our stall speed is quite high. That means takeoff speed must be higher, thrust must be higher, unless we get some magic way to increase CL max. And finally, the aircraft must deploy from a stowed configuration. Well, that means every single part of the aircraft has to be remotely actuated. That means in addition to your standard 6 channels to control the aircraft, we need 1 channel per store, 2 channels per folding mechanism, 2 channels per locking mechanism. Pretty soon we need over 40 channels of remotes when a typical aircraft radio is only about 8 to 14 channels. It's a lot to take in, but fortunately we have some method to the madness. There is an optimization process which takes the majority of the year. The first 2 boxes are the mission interpretation and then requirement synthesis. And we've been in this loop for quite a while. It's you size the aircraft and then you test it, you verify it. And then you repeat this process by continuing to refine your weight and your drag estimates until you get a final optimized aircraft, hopefully at the very end. And this has been our design so far. The power requirements, we managed to get around the wing limitations by doing 2 folds. Because it has to fit in a 3 foot box, if we make the center section 3 feet and have the wingtips fold 1.5 feet, we only require 2 folding mechanisms, which simplify design. In addition, the 1.5 foot wingtips also require less folding force. These only require the linear actuators to expend 16 ounces of force, whereas an additional length increase would increase the moment, the force would increase exorbitantly. And finally, we determined that a maximum of 10 stores was what we could realistically take off and carry the flight pack. Beyond that, we were power limited or had to fly at an uncomfortable top speed.
Hence, from the propulsion aspect, which consists of the main propeller, the motor, the ESC, and the battery combination, we really had to test multiple configurations with different motors. So ultimately, we ended up settling, well, the prop's not on there right now, a 19-inch prop paired to a 275 kV motor to be able to spin that massive prop, as well as an ESC that had a high enough voltage and current limit to make sure that the power or the thrust delivered from the motor and the propeller itself was not being restricted in any way, because we were fighting to make sure that we could even make takeoff in the past, but that seems to have been resolved.
Now, testing. We've designed a plane, we've sized it, and we have some initial configurations, but we have to make sure that the numbers that we've been working with the past year aren't junk. That's done by flight tests. Now, for example, the drag buildup I did initially was just purely calculations. It was all theoretical. It used geometric features of the plane like span, like wetted area of the wing, coefficient of drag estimations for the store, for the tail, interference factors, all gotten from theoretical textbooks. And we arrived, or I arrived, at a total CD naught of around 0.0175. This basically translates to needing about 400 watts during cruise and about 1,000 watts during takeoff.
Now, the flight tests themselves proved to seem like there was a little bit more to the story than we had originally calculated. So in order to make sure that we got consistent data from the aircraft itself after testing its individual components, we employed the use of a Pixhawk 4 unit, which is essentially like an autopilot system. It's not allowed during the competition, but we'll remove it before then. But the main point is the Pixhawk allows us to control things like the airspeed, the altitude, the flight control systems, to maintain a steady level flight condition. We need this in order to maintain consistent power data, as you can kind of see in the plot above on the top, that as the Pixhawk controls the aircraft and flies the laps it's programmed to do, it's trying to maintain a constant speed of about 55 feet per second. The voltage does drop, that's the red line, a little bit, but that's just because it's trying to maintain the speed it was programmed to do. Overall, what we found out is that the takeoff power is a lot higher than initially expected, at about 1,600 watts as opposed to 1,000 watts, likely due to the inefficiencies involved in the system, and the cruise power was raised to about 600 watts as opposed to the original 400. PICSOC helped us refine the efficiency and those constant values from the original guess, or estimations, I should say, in our drag development, that all contributed to making sure that we can build or carry more stores ultimately in the end.
And that about wraps up propulsion testing. We also had to validate the structure of our aircraft was sound to withstand certain loads. Now, wings are loaded elliptically, or ideally they do, but we determined that our aspect ratio was large enough that we could approximate an elliptical lift distribution. So we took a prototype wing and made a wing jig test stand. It clamped it at the end to simulate how it would be anchored at the root of the wing. Next, we weighted sandbags at specific increments in order to match an elliptical lift distribution, of which we got by using AVL, which is a vortex lattice program that basically plots CL as a function of span. We use this information to get loads for those sandbags and increase them in terms of Gs, because that's typically how the competition determines load failure, and increased it till it failed. In this case, we determined that it failed because of excessive deflection. If your aircraft deflects and twists too much during flight, there is a strong possibility that your control surfaces actually reverse their functions, in what's called aileron reversal. For our case, the wing deflected 7 inches before we deemed it too much. But it took 4 Gs, which is around 34 pounds. This is a lot more than we expect. It's just about 2 Gs, I believe, for the competition requirements for the wing to test. So it is a bit overbuilt. But the important part is that the wing locking mechanism, the wing joint, did not deflect.
We do have a flight test plan, but unfortunately we are running a little bit low on time, so we'll be skipping ahead to more of just like the manufacturing budget and moving forward from there if there's time available.
Now, manufacturing, typically we use a lot of balsa construction. This case, a lot of the prototyping, because there was a lot of fine mechanics involved, were made using 3D printed parts. 3D printing allows just rapid prototype production, allows very accurate dimensional reproduction. We use a lot of composite tubes too. Most of our composites this year were pre-made, but historically we have done things like molding. Wings were typically molded in the past using fiberglass and epoxy. But of course, it's one thing to design and build the aircraft. We also need a team to manage it.
Right, so the team involves a hierarchy structure consisting of the chief engineer at the top, along with the project manager and all the faculty advisors, followed by all the sub-teams who essentially take the guidelines from the chief engineer, again referred to from the rules, that passes down to the project manager to be communicated down to the team to try and meet those requirements. With that being said, here's the Gantt chart that the team has followed and where we see ourselves in the coming spring quarter, most notably with the design proposal due last October, the design report, which is actually due tomorrow, and our competition mid-April. Last but not least, we have our budget breakdown that we've spent so far in the competition and where we see ourselves spending a little bit more in the future. So key takeaways would be, again, because the scale of the aircraft as it is requires a lot of components. A lot of time and money has been spent in terms of buying fabrication materials and electronics in order to power the systems. And most notably, after all the manufacturing and testing is done, the competition will require a little bit of money for transportation and accommodations. But with that, you have any questions?